All right, so today I'm going to talk about orthogonal or orthonormal bases for a vector space. And I just want to quickly recall something that we talked about last time. So when we were talking about projections, there was kind of a special case where if we were trying to project a vector onto a line, so here's vector B, this is the line L that I'm projecting onto. And let's say we had a vector, which I'm going to call A, which lied along the line L, okay? Okay, so the projection of B onto the line L was represented by this red vector, which I'm just going to call P right now. Okay. All right, so P, it's the projection of B onto the line L. And I mentioned how in 2415 and 2419, for those of you who have taken those calculus classes, you would have learned this as the projection of B not onto the line L, but onto the vector A. But they turn out to be the same thing. And the formula for this, it was equal to A dot product with B over A dot product with itself. So all of that is a scalar, and all that multiplying the vector A. And so that was the formula for the projection of B onto the vector A. And I want to create some notation for this, so I'm going to denote it as a projection of B and onto A. So I think this is how it's denoted in the other classes. So this, I'm going to follow that convention for this class as well. Okay. And so the projection vector, it's the vector that makes like a perpendicular with the line L, okay? All right. Now, I was going to talk about having an orthogonal or possibly an orthonormal basis for a vector space. So we've talked about what a basis is. So it's a collection of vectors that both spans your space and is linearly independent. So an orthogonal basis for a vector space, as the name suggests, it is simply a basis for your vector space in which all the vectors are orthogonal to each other. Okay. And so the prototypical example of having an orthogonal basis is the standard basis vectors. Okay, so here, just working in R3 for a specific example. So if you remember, these three vectors were known as the standard basis vectors for R3. So these guys, they happen to form an orthogonal basis for R3. Okay, because they are a basis for R3, and in addition to that, they are all orthogonal to each other. And you guys remember how to check if two vectors are orthogonal to each other? Yeah, so check the dot product, and in this example, you can see that if you take any of these vectors and you dot it with the other, the dot products are going to return 0. And since they're all like orthogonal to each other, all right? So that is what an orthogonal basis is. Let me also touch on orthonormal. Okay, so to have an orthonormal basis is one in which it is an orthogonal basis. And all of the vectors in the basis are unit vectors, meaning they all have a length equal to 1, or unit length, if you will. Okay. So the standard basis here, not only is it an example of an orthogonal basis, but it is in fact also an example of an orthonormal basis as well, okay? Because not only are these three vectors all orthogonal to each other, but all of them are unit length, meaning their lengths are all equal to 1, okay? So the standard basis for Rn is a prototypical example of an orthonormal basis for a space. All right. So orthogonal and orthonormal bases, they are a little bit more special than just like any ordinary basis. So here I wanted to just give one reason for why having an orthogonal basis has its advantages over like a regular, not necessarily orthogonal basis, okay? Okay, so let's say that we have some basis, and let's just work in R3 for a specific example. I'm just going to make up some numbers right now. All right. So here, let's just take it for granted that This is a basis for R3. But right now, let's note that it is not an orthogonal basis. Okay. So if you do the dot products between these vectors, they are not going to give you all zeros. So they are not orthogonal. Now, because they're a basis for R3, then in particular, they do span R3. If I take any other vector of R3 right now, okay, so I should be able to take this vector B, and I should be able to express it as a linear combination of the vectors v1, v2, and v3. Okay. So that means I should be able to find some constants, C1, C2, and C3, for which this would be equal to the vector B. And if I wanted to solve for these scalars, C1, C2, C3, to solve for C1, C2, C3, I would ultimately have to set up a system of equations. Oh, whoops, I skipped to the end, but that's okay. All right, so to solve for C1, C2, C3, I would ultimately need to solve this system of equations here in order to get the coefficients, okay? Now, if I had an orthogonal basis, then it turns out that you can solve for these coefficients without solving the linear system of equations, as you would have to do in this example here for a non-orthogonal basis. All right, so let me try to explain how you could do things differently if you had a basis that was orthogonal. Okay, so here there's no need for me to use specific numbers for this, so I'm just gonna say, let's suppose we have these three vectors, v1, v2, v3, and they form an orthogonal basis. Okay, so again, if I take any vector in our space, I should be able to write it as a linear combination of these basis vectors. Okay. All right. And then if I wanted to solve for C1, C2, and C3, rather than setting up a system of equations like I had to do over here, there is something else that we can do. And so I'm going to illustrate what that something else is. So let me take this equation over here. And I'm going to apply a dot product on both sides. I'm going to dot both sides with the vector v1. Okay, so if I do that, And if I distribute the V1 into this parentheses over here, so I'm going to get V1 or C1 and then V1 dot product with itself. Okay. So that's just distributing to the first term. Now the second term, we're going to get V1 dot product with V2, and that would actually be equal to 0, since we're assuming that V1 and V2 were orthogonal to each other. And same when I end up getting V1 dot product with V3 over here. That dot product will also be 0, again because these formed an orthogonal basis. All right, so then from this equation, I can actually just solve for C1 now by dividing both sides by this quantity. So what we end up getting is that C1 would equal V1 dot product with B over V1 dot product with itself. Okay. So this little trick of dotting both sides by V1 actually allowed us to solve for C1 and even come up with a relatively simple formula for it. And you can kind of do the same thing. If you dot both sides of the original equation by V2, you would find this formula for solving for C2. And likewise, C3 will turn out to equal V3 dot product with B over V3 dot product with itself. So that's kind of interesting that when we have an orthogonal basis, we were able to solve for these coefficients over here without needing to solve a linear system of equations, as we would have to do if we had a non-orthogonal basis. And so that illustrates one of the advantages of having an orthogonal basis, okay? Yes, all right. So in addition, if our bases were orthonormal, then things will simplify even further. So if orthonormal, then V1 dot product with itself. So remember, this is equal to the length of a vector squared. So because they're orthonormal, the length in particular must be equal to 1. And same for V2 dot product with V2 and V3 dot product with V3. So the formulas will simplify even further to be that C1 is simply V1B, C2 is V2 dot product with B, and C3 is V3 dot with B. Okay, so then that's again if they were in fact orthonormal. Right. Okay, now I'll mention one more thing, which is if you look at these formulas that we did end up getting for the coefficients. So let's say I plug them back into the equation. So these were the coefficients for expanding B as a linear combination of V1, V2, V3. So then if I plug those formulas in, what we end up getting is that, so C1 was V1 dot with B over V1 dot V1. So it's that times V1 plus, and then just to save some time, I won't write out the rest, but we can plug in the formula for C2 over there and for C3 over here. And if you look at this expression, you should notice that this is actually just the projection of B onto the vector V1. Okay. And then likewise, this over here would have been the projection of B onto V2. And likewise here, this would have been the projection of B onto V3. Okay. So this is kind of like an easy way, I feel like, of remembering, I guess, like all these results that we just proved. So basically, if you have a orthogonal basis, then to expand a vector in terms of a linear combination of the basis vectors, you just have to project it onto each basis vector. And that will give you how to write it as a combination of the basis vectors, okay? All right, so that illustrates one advantage of working with an orthogonal basis. But now what we want to be able to do is, given some vector space, we want a way of being able to find an orthogonal basis for it. And so that's where the Gram-Schmidt algorithm, I'll call it, comes into play. So I'm going to talk about what Gram-Schmidt is. So I'm going to abbreviate Gram-Schmidt as simply GS. All right. So Gram-Schmidt is I guess a procedure, I'll call it, or an algorithm. Oh, sure, let's use the word algorithm. So it's an algorithm for taking a basis for a space and I guess producing from that basis an orthogonal basis. Okay. Okay, so then a little bit more symbolically, if I have like vectors v1 to let's say like vk, and these are some basis for some space v, not necessarily orthogonal. Then what the Gram-Schmidt algorithm will do is it'll take these vectors and after doing some computations, it's going to produce a new set of vectors, which I'll call W now. And then this new set of vectors will not only still be a basis for V, but in fact, it will be an orthogonal basis for the space V. All right. Once you have an orthogonal basis, if you want an orthonormal basis, then you can always take your orthogonal basis and simply normalize each of those vectors by dividing by their length. And by doing that, you'll end up with an orthonormal basis after that. All right, so I'm going to do an example. So I'll outline what the Gram-Schmidt algorithm is, and then I'll do some examples of applying it to some problems. Just before that, any questions about anything so far? Okay, all right. All right, so this, being able to find an orthonormal base for a space, that is going to come into play for some topics that you'll be learning towards the very end of the semester. So it's possible that you may need to do this Gram-Schmidt algorithm when you're finding a spectral decomposition, or perhaps a singular value decomposition of a matrix. Okay, so here's the Gram-Schmidt algorithm. So I'm just going to outline the steps to the algorithm. Okay, so again, you start with some basis, V1 through Vk. It's probably not orthogonal. If it's already orthogonal, then there's kind of no point to doing Gram-Schmidt. So we'll assume that's not orthogonal. And then, as I said, it produces an orthogonal basis, which I was calling W. It's W1 to Wk. So here's how the algorithm works. So W1, the first vector that the algorithm produces, is simply going to be equal to V1. Okay? All right, so next, vector W2. So the way that you get W2 is you're going to take V2 and you're going to subtract from it its projection onto W1. All right. Okay, so you might remember when you took a vector and you subtract its projection. So you guys were, I think in your homework assignment, that was like referred to as your error vector. But remember, in general, when you take a vector and you minus its projection, that error vector is going to be orthogonal to whatever space you were projecting onto, or in this picture, whatever vector you were projecting onto. So the idea is, since I'm subtracting the projection of V2 onto W1, therefore W2 should be orthogonal to W1, okay? Then after that, if you want a third vector, one which is orthogonal to both W1 and W2. So what we can do is take the vector V3, so the next vector in the original basis, and then subtract its projections onto W1 as well as W2. So by subtracting its projections onto both W1 and W2, that will guarantee that we have a vector that's orthogonal to both W1 and W2. And then that would just continue the same pattern. So to get V4, you would take V4 and subtract its projections onto W1, W2, and W3, and then so forth and so forth. So it gets pretty long after a while. So my feeling is you would rarely ever have to go beyond 3 steps of the Gram-Schmidt algorithm. I would say like almost guaranteed you wouldn't go past 4 just because it gets so long after a while. Okay? So those are the formulas for getting the Gram-Schmidt basis. And then again, if you're looking for the orthonormal basis, then once you get this orthogonal basis, you can just normalize all your vectors, and you have an orthonormal basis now. Excellent question. So what should you do with all the square roots that you would get? So, it's a little bit unfortunate. Well, okay, so for the Gram-Schmidt procedure, when you're getting the orthogonal basis, you actually probably won't have that many square roots because remember that in the formula for projection, you're dividing by like, V1 dot with V1 and things like that. And that's the norm squared. So like because it's getting squared, that actually gets rid of the square root. Now, in regards to normalizing your vectors in orthonormal basis, then yeah, that's a little bit unfortunate. Because when you divide by the norm, you would typically pick up a square root from that. Now, I guess fortunately, you won't need to do too much computation, I feel like. Yeah. At least in the like applications that I'm kind of thinking of in my head, for what you'll be doing later in the semester. You won't need to do too much computations really with your orthonormal basis. You'll just need to actually like compute them so that you have them and that you know them. So in that sense, it's maybe not so bad to get a bunch of square roots because you won't need to do too much with them. Okay. All right. All right, great. So then let's look at some examples. Okay. All right, so for this first example, let's say we have a plane in R3. Let's say the equation of the plane is x minus 2y minus z equals 0. And I want to find an let's say that I want to find an orthonormal basis for this plane. Okay. So to do that, what I'll do is I'll first just find a basis for the plane. So in order to get a basis for the plane, what I can do is here I have just one equation. So I'll be able to solve for one of my variables, and the other two variables are going to be free variables. So in this case, I'll choose y and z to be my free variables. In which case, solving for x, we will get that x is 2y, so 2s, and plus z, so plus t. So then if I write it out in kind of my usual way, So as a vector, we'll say that vector xyz must be equal to s times the vector 2, 1, 0, and plus t times the vector 1, 0, 1. So this shows us that for a vector to be on the plane, it has to be a linear combination of these two vectors. So what happens is that these two vectors end up giving us a basis for the plane. Okay, so you should recognize this procedure. So I'm essentially finding the basis for the null space of a matrix. So I guess specifically the plane was really the null space of this matrix of coefficients in our equation. So because the plane is the null space of this matrix, it's not surprising that getting a basis for it resembles getting a basis for the null space of a matrix, okay? All right. Now we have a basis for the plane, but we wanted an orthonormal basis. Okay, so this here is going to be like my vectors v1 and v2. And what I'm going to do is I'm going to apply the Gram-Schmidt algorithm to these basis vectors. So the Gram-Schmidt algorithm will produce an orthogonal basis, W1, W2. So the way that Gram-Schmidt works is the first vector in my orthogonal basis, W1, should be equal to V1. So the first one's always easy. So for us, W1 will be the vector 2, 1, 0. And then to get W2, so to get W2, we take V2 and we minus its projection onto W1. So let's do those computations and let's see what that will give us. So it's going to be, here's V2, 1, 0, 1, minus. Okay, and I guess I'll write out the formula for projection here. So we do V2 dot W1, then it's over V2, over W1 dot W1, and then times W1. Okay, so that's the formula for the projection. So I want to do right now dot product between V2 and W1 for my numerator. So V2 dot product with W1 is going to be 2 plus 0 plus 0. In my denominator, it should be W1 dot product with itself. So that's going to be 4 plus 1 plus 0. And then all of that should be multiplying the vector W1. So multiplying the vector 2, 1, 0. So then if I do this computation, that's 1/2 of 2, 1, 0. So 1 minus half of 2, 1 minus 1, which is 0. 0 minus half of 1 will be minus 1/2. Then 1 minus 0 is 1. So I think that's what we will get for W2. Yeah, you are correct. Yep, thank you. I think I even said 4 plus 1, but 4 plus 1 is 5. That's right. Oh, okay, so it's just 2/5 now. Okay, so then let's just recompute that. So if we do this, 1 minus 4/5 is 1/5. 0 minus 2/5. Then 1 minus 0 is 1. Okay. All right, very good. Okay, so then we have now the vectors W1 and W2. So they should give us an orthogonal basis. For the plane. Okay. Now you can always double check if you did your computations correctly by verifying if your vectors are orthogonal to each other. So if you check W1 dot product with W2, so you should find that the dot product does in fact equal 0. So they are in fact orthogonal as they should be if you do all the computations for Gram-Schmidt correctly, okay? Okay, so then finally, the question was asking for an orthonormal basis for the plane. So I'd have to do now is take the orthogonal vectors that we have, and we'd have to normalize them in order to make them unit length. Okay, so for instance, if I take the vector W1 and I divide it by its length, so its length would be the square root of 5. So that will give us the first vector of our orthonormal basis for the plane. All right, and then to normalize W2, so I don't like having fractions, so what I might do is just kind of scale this vector by 5. And then after scaling by 5, then I will normalize it. So divide it by its length to get a unit length vector. So 1, -2, and 5. If I compute its length, it's going to be the square root of 30. So 1 plus 4 plus 25. And then I could use these two vectors, q1 and q2, for the orthonormal basis for the plane. All right, so any questions about that procedure? Okay, all right. So I'll do another example now, but this time finding an orthogonal basis. For this band, of the vectors, so 1, 0, negative 1, 0, 4, 1, 0, 1, then 1, negative 4, 5, and 2. Okay. All right, now, so these three vectors that I've written out here, so let's just take for granted that they are linearly independent, all right? So that, in fact, they form a basis for their span, okay? So we have a basis already, but again, if you check like the dot products right now, they're not orthogonal to each other. So that is not the case. So asking for an orthogonal basis is not the same as asking for the orthogonal complement. I can touch on finding the orthogonal complement pretty quickly though, so maybe after this example, I'll just briefly touch on that. Yeah, okay, all right. Okay, so here we've got a basis for our space, but it's not an orthogonal basis. So again, what we'll do is we'll just apply the Gram-Schmidt algorithm. To get an orthogonal basis. So this time there are three vectors. So I'll need to do like one extra step in the Gram-Schmidt algorithm. So we'll just kind of see how that works in this example here. Okay, now remember for Gram-Schmidt, the first vector W1 is simply equal to V1. All right, so next, in order to get the second vector, W2, we take V2 and we minus its projection onto W1. And the projection onto W1, we're going to do W1 dot product with V2 over W1 dot product with itself. So let's do those computations. So I'm going to plug in, so V2 is the vector 4, 1, 0, 1. So now I need W1 dot product with V2. So here's W1, here's V2. So the dot product will be 4 plus 0 plus 0 plus 0. Okay, so we got 4 in the numerator. All right, W1 dot product with itself is going to be 1 squared plus 0 squared plus 1 squared plus 0 squared, so 2. So it'd be 4 over 2 and then times W1. Okay. So if we finish the computation, 4 minus 2 is 2. 1 minus 0. 0 minus a negative, so plus 2. So I think it's going to be that. Minus 0 will be 1. Oh, and then let's check. I think I messed up. 1 minus 0 is 1, not 0. So let me fix that. Okay. So then that should give us vector W1. Yeah, I think that's all good. And then if you just want to check right now, W1 and W2 should be orthogonal to each other. So if you just check their dot product, you should find that their dot product is equal to 0. So that means that what we got for W2 looks pretty good right now. Okay. So lastly, we need to get one more vector, W3. So to get W3, we take V3 and subtract from V3 its projections onto W1 and W. So its projection onto W1 and then its projection on W2 over here. All right, so let's plug everything into that formula. So first, it's going to be V3. So I'm going to just copy down my V3. So next we have W1 dot product with V3. So if we dot V3 with W1 here, it's going to be 1 minus 5. So I get negative 4 in that numerator. W1 dot product with itself is equal to 2. So times W1. And then minus, and then let's do W2 dot product with V3. It's 2 minus 4, it's negative 2, plus 10 is 8, and plus 2 is 10. So that was the numerator. W2 dot product with itself. So 4 plus 1 plus 4 plus 1 will be 10. And then times W2, so times this vector. All right, let's finish the computations here. So looks like we got 1 plus 2, so 3. Minus 2 will be 1. Negative 4 minus 1. So I think that's negative 5. So here 5 plus negative 1 or negative 2 is 3. Minus 2 is 1. And then 2 minus 1 is 1. So that's what I end up getting for W3. So we can check if that seems reasonable. So W1 and W3 should be orthogonal. So if we do the dot products, that does check out that their dot product is 0. It should also be orthogonal to W2, so let's also try dotting it with W2 real quickly. 2 minus 5 is negative 3, plus 2 plus 1. So yeah, I think that looks good. Yeah. Okay, so you don't have to check, but I think it's useful just to verify that your vectors that you're getting are orthogonal to each other. Okay, so the vectors W1, W2, and W3 that we ended up getting would give us an orthogonal basis for the space that was spanned by the original one, V2, and V3. Okay? And you could normalize all of them if you wanted an orthonormal basis, but I will end the example with that, okay? All right, so any questions about that? Anything in that example? Would the order of finding W3 matter? So are you talking about where you subtract its projection onto W1 and then also onto W2? And maybe, okay, yeah. So no, it wouldn't matter if you did the subtraction the other way around. You should still get the same result. Okay. So I'll say a couple of things and then I'll address the orthogonal complements as well. So just a quick note, what would happen if these vectors were not linearly independent? So if they were not linearly independent, meaning they would not have been a basis, what happens when you do Gram-Schmidt is one of these vectors that you end up computing would end up being equal to 0 if the original vectors were not independent. And when that happens, you can just take that 0 vector and just like throw it out because it's like just irrelevant. So in that sense, it doesn't really matter if your vectors are independent or not. If they're not independent, you'll just get some 0 vectors when you do Gram-Schmidt, and you'll just like ignore them because they're all 0, so they don't matter. Okay. Okay, so I think that's all I'll say about Gram-Schmidt. And then, small aside, I'll just kind of talk about finding the orthogonal complement of a space. Okay, so let's just consider an example. So let's say that we were to find the orthogonal complement to the span of, let's just use 2 vectors here. So let's say you wanted to find the orthogonal complement to the span of these 2 vectors. Okay. So a pretty simple strategy for this is, so if you recall, when we were talking about the fundamental subspaces of a matrix. One thing that we talked about was how the row space and the null space of a matrix, these are orthogonal complements. So the strategy for these types of problems, one strategy would be to take a basis for your space. So in this case, these two vectors would form a basis for their span. Because we can see they're not multiples of each other, so they are independent. So I take these basis vectors and I put them into a matrix as rows, okay? So by doing that, the span of these vectors would now be equal to the row space of this matrix A, okay? And so now that the span of these vectors is the row space of this matrix, if I want to find its orthogonal complement, I now know the orthogonal complement would be the null space of this matrix. So then I would just find the null space of A for the orthogonal complement. Okay, very good, all right. And let's see here, there's not much time left. So let me think what I will do. I could start on determinants, but I think since there's only about 10-ish minutes left, I think I'd rather just wait until next time and just like start at the beginning with determinants instead. I could talk a little bit more about Gram-Schmidt and orthogonal basings and stuff, but I don't think 10 minutes is enough time to touch on anything else per se. And I don't think it's like super important either. So I think I'll actually just end my review a little bit early today instead. Okay. And I think this is going to be the first time since maybe the very first review this semester that I was able to end early. All right, so to answer that question, how does an orthogonal projection differ from a normal projection? So in this class, it does not. So whenever someone talks about a projection in this class, it's always talking about an orthogonal projection. Now, there is such a thing as, I think what I've seen people call an oblique projection. The idea is, okay, so let's say, so here I'm going to create an orthogonal, oh, I guess it's an orthogonal basis. And then let's say I have some vector B, okay? And so I talked about how before that, to express B as a combination of V1 and V2, as a combination of V1 and V2, it would simply be its orthogonal projection onto V1, and then plus its orthogonal projection onto V2. And so these projections that we're talking about, they're specifically orthogonal projections because of this right angle that the projection makes. Okay, but if I had another situation where our basis was not orthogonal, and I try to mirror the problem that we had. So here's vector b1, or just b, sorry. Okay, so I talked about how if we want to express b as a combination when our basis vectors are not orthogonal, then it's a little bit harder to for C1 and C2. Because we'd have to solve a linear system of equations. But like, this vector would be C1, V1. And then this would be like some scalar C2 times V2. And so these vectors are no longer the projections of B onto V1 or V2, or at least not projection in the usual sense that we have thought of it. Because here the projection doesn't quite make a right angle with between like this error vector with V1. So we could maybe think of C1, V1, and C2. We can still think of them as projections though, like a projection of B onto V1, V2. But this would be like a non-orthogonal projection. Because it's not making a right angle here anymore. So that's kind of the idea, I suppose. So you can certainly talk about projections which are not orthogonal, especially when you have like a non-orthogonal basis like we have here. And so that's just maybe interesting to see, but I don't think you guys would do anything with them in this class. Excuse me. Okay.